Hi everyone. In this video, we'll explore deterministic finite automata, or DFAs for short. These are simple yet powerful machines that helps us determine if a string follows a set of rules. They're used in real-world applications like traffic lights, vending machines, search engines, even compilers. Let's break it down step by step. Okay, so simply a deterministic finite automaton is essentially just a machine that determines if a given string belongs to a specific language. Simply, it helps us decide whether or not a particular sequence of inputs follows a predefined set of rules. Now, a DFA is made up of five key components. Those are the finite set of states, usually symbolized as Q, a capital Q, the alphabet, which is the finite set of input symbols that the DFA can process. Then we have the initial state, which will be the starting point of the DFA. It is also a subset of the finite set of states. Now, the initial state will always be just one state. We're not allowed to have multiple initial states. Whereas the final state, which is the next key component, it's a set, so it could essentially it could be one state, it could have multiple states. Usually it's one state, but you will see a lot of examples where there are more than one final state. And the final state is going to be the condition where a string can be accepted. Then we have the transition function, which describes the functionality of the DFA. It shows for every state given an input, what happens to the state. Do you stay in the state or do you go to a different state? Okay, so we're going to first look at Q, which is the finite set of states. So, just as I mentioned earlier, it is simply just the set of all states in the DFA. So, you really don't need to there's no preconditions that need to be satisfied for a state to be in queue. You literally just put all the states in queue. Now usually queue will be provided in problems. You wouldn't normally have to find queue, but it's really not that hard. It's just if we look at the example on the right, you can see that Q is simply the set of all states. It's S0, S1, and S2. Then we've got the alphabet, which is the finite set of input symbols. This is going to be what symbols the DFA can read. So in our example here, we can see that the DFA can read zeros and ones or binary strings. This could be anything really. It could be even letters. It could be A and B, X and Y. It could be more than just two. It could be 0, 1, 2, ternary strings. Yeah, you just need to specify what it is that the DFA can read in the alphabet. So in our example here, it's 0 and 1. Then we have the initial state, which is the landing point of the DFA. Whenever you begin processing an input, you will start at the initial state and then you'll take it from there. Then you'll start reading whatever it is that the first input is. Now, just like I mentioned before, the initial state is obviously a subset of Q, big Q. Since it is a state, it will be in the set of all states. Then we've got the final state or the set of final states, because just as I mentioned earlier, we could have multiple final states. And even if you just have one final state, you should still have it as a set. And then you would just have the set of final states, which just includes that one final state. Because the F is a set, it's not just a state. So, yeah, final states, also known as accept states, are where the DFA ends after processing a valid string. Meaning, if you finish processing your string and you happen to be at a final state, then that string is accepted. And if you finish processing your string and you don't end up in a final state, then that string is rejected by the DFA. Then we have our transition function, which is the functionality of the DFA. It explains for every given state what happens when it reads a specific input for every input. So in our example here, we have obviously our only two inputs are 0 and 1. So we'd have to show for every state in the DFA, meaning S0, S1, and S2 in our example, what happens when you read 0 and what happens when you read 1 for every state. So we can see S0, for example, when it reads 1, it goes to S1. When it reads 0, it stays in S0. Then we see that S1, when it reads 0, it goes to S2. When it reads 1, it goes back to S0. And S2, when it reads 0, it goes to S1. And when it reads 1, it stays in S2. So in your transition function, you'd have to specify that for all the states in the DFA. Now, in our example, there's only 3 states. You can imagine if you've got 4, 5 states, your transition function is going to look bigger than this. If you have more inputs, it's going to look bigger as well, because obviously if we, for example, took in this set of ternary strings instead of binary strings, which means just the inputs are 0, 1, and 2, then we would obviously have a bigger transition function as well. Okay, so now here we look at an example where we're asked to design a DFA that recognizes strings with an even number of ones. Okay, so I already have the DFA here, but I want you to, when you approach these problems, always try to think of the simplest string that could be accepted by your DFA. So we're asked for a DFA that accepts an even number of ones. What is the most simple input string that satisfies that condition? Well, that's the empty string. If you have an empty string that literally has no inputs, that does satisfy the condition because it technically has 0 ones, and 0 is an even number, therefore it should be accepted. So that's why you'll see that my initial state in this case is actually also my final state, because if someone was to use the empty string as an input, it should hypothetically get accepted by our DFA because it has an even number of ones. Then another simple string that should be accepted by our DFA is just 0. If someone just has 0, like literally just the number 0, it should be accepted because it still has a 0 number of ones. Then we should start looking at, okay, when is it that our machine should reject a string? Well, if the condition for it to accept a string is if a string has an even number of ones, then it should reject a string that has an odd number of ones. Therefore, if you're in the initial state, which also happens to be our accept state, and you get 1 as an input, you should go to another state that's temporarily rejecting your string. So we can see that Q0, upon getting input 1, goes to Q1, which is not an accept state. Because if our string would have just finished there, it shouldn't get accepted because 1, 1 is odd. You'd have to have an even number of ones to get accepted. So you'd go to another state and only be allowed back to the final state if you were to get another one, making it an even number of ones. So that's what our DFA is doing here essentially. We've got our initial state, which is Q0, and right away it's an accept state. Just like what we said, if it's empty, it should get accepted. Then we have a self loop for zeros. So whenever you get a 0, you can stay in Q0 because the number of zeros doesn't affect the string in this case. You could have an infinite number of zeros. As long as the number of ones is even, you will be accepted. But the second you get 1 as an input, you will go to Q1 because 1, 1, meaning like just a 1, is an odd number of 1. So you should go to Q1 and only be allowed back to the accept state once you get another 1, meaning you've got an even number of ones. And you will see that we also have a self loop here for zeros at Q1, because similar to how zeros didn't matter when you were in the accept state, zeros don't matter when you're in Q1. You could have an even number of zeros, you could not have zeros from the first place, you could have an even number of zeros. It doesn't matter because what we care about is ones here. And then the second we get another 1, making it an even number of ones, we're allowed back to the accept state. And we will look at some of the accepted inputs here. So obviously if your input, we set the empty string, and then if you've got just a 0, that's an even number of ones, you're accepted. Double 0, same idea. Then like 1 would be rejected. So if you go to 1, just 1, you've got an odd number of 1, you wouldn't be accepted. 1, 1 would be accepted because 1 takes you to Q1, and then from Q1, 1 takes you to Q0, which is an accept state. Then 1, 0, 1 is also accepted. 1 takes you to Q1. Q1 loops on 0, so you stay in Q1, but then you read another 1 and you go back to Q0. Now you're accepted. Then we look at a bit of a longer string, but the same idea holds. We have 0, 0. Okay, so you start in the initial state, you read a 0, you're still in the initial state. You read another 0, you're still in the initial state. Okay, now you read a 1, you go to Q1. You read another 1, you go to Q0 again. You read another 1, you go back to Q1. Okay, now from Q1 you read a 0, so you loop and you stay in Q1. Then the last symbol is a 1, so you go back to Q0 and the string is accepted. And we can confirm this just by looking at the string. We can see that there's 4 1s, which is an even number of 1s, and the string got accepted. So we can see that our automaton holds up for the condition. All right, so that's how deterministic finite automata work. They're essential tools in computing used to solve problems and power systems we rely on every day. Thanks for watching.